Hello, everyone. Welcome back. Today, I'm recording the lecture in my office. I'm also going to use my iPad to advance the slides and also make annotations. Okay, let us get started. Today, we're going to talk about lecture 5, Gibbs equilibrium thermodynamics and the characteristic functions, enthalpy and free energy. We showed this photo before. Was made by Maxwell in 1874 and talk about presents the internal energy as function of entropy and volume, as energy and entropy and volume. And this photo was taken at the Cavendish Lab, University of Cambridge in 2022. This equation, this function is a characteristic function. It's internal energy as its function of as a variables of entropy and volume. It's for a closed and equilibrium system. So what does it mean? That means there's no mass change, dni equal to 0, and the dxi equal to 0. There's no driving force. There's no process, internal process happening in the system. So then we get the entropy change of the system would equal to dq over t, because no mass change, no internal process. So there's only one term left for the entropy change of the system. So maybe if you remember that, what we had before was that the ds is equal to dq over t plus a summation of all the mass added, and then plus the dxi. Okay. But now we only have one term because this term equals 0, that term equals to 0. Then for simplification, Gibbs only considered hydrostatic work. That means we have dW now, only one term. There's no electrical, no magnetic, and no other work, not types of work. Then the combined law we derived before becomes only two terms now. Okay, entropy heat, so because now we have dq equal to TdS. So you replace in the combined law, you get a TdS minus PdV. So it's closed and equilibrium system. Now, if we then Gibbs moved to consider open system, but still at equilibrium. Now we had one more term. Now we get the entropy of each component. SI, we call it partial entropy. Now we have to add another term, the energy to the combined law. Okay. So Gibbs introduced a new concept called chemical potential, but he directly included this one. He showed that, okay, because the mass adds in must have energy, right? So he added another term, chemical potential. So that's the direct introduction. You get a mu I. So each component has an energy, some energy, got a chemical potential. You can say it's chemical energy too. And then the internal energy becomes a function of three variables: entropy, volume, and Ni. Ni is one variable for each component. So we call them natural variables. It's because they naturally show up from the combined law. So let's look at the chemical potential. Remember that in previous lectures, we derived the chemical potential as function of partial internal energy minus T times the partial entropy of the component. So that's the equation which Gibbs presented in 1870s. Now we can define the chemical potential by this equation too. So now, because you fix the first, you will say entropy is fixed, volume is fixed. Okay, the components of other most of other components fixed. So I have dnj, j is not equal to I equal to 0. Okay, so that's chemical potential. However, remember that entropy also is related to the partial entropy too, right? So we have this relation, S is a function also dni. That means if you fix S, you have to change heat because you have dni is not equal to 0. So that's a heat exchange one must have between the system and the surroundings. So what it means is that, so if we add dni into it, okay, we have to remove dq to make ds equal to 0. Okay, so that's the constraint we have. Of course, volume is still okay, right? We can see fixed volume. If we fix volume, we know that if I add mass into it, so because dV equal to 0, when you have dV equal to 0, because there's no change of volume, right? Fixed volume, and you add mass into it, then pressure must go up, right? Inside the system. Okay, but you can fix V. So V and Nj can be independent, but S cannot. Okay, if you want to keep S, you have to do something with the surroundings. Okay, but you can fix V without any exchange with the surrounding because you can just increase the pressure inside the system. Okay, so that's very different, right? Because the concept here is that if we want to fix the entropy of the system, you add mass into it, then you have to make another exchange with the surroundings. Okay, but you can keep the volume constant. There's no exchange without exchange with the surroundings. Okay, because you can increase internal pressure. So that's very different concept. That means S and V, S and Nj, or any N, they are not independent. You actually cannot treat them as independent variables because of this relation. Okay, so the Max really emphasized, Max Hillard emphasized that we really want to separate the two types of quantities in this combined law, okay, called the potentials and molar quantities. Most people, including me, before I learned the thermodynamics third time from Max Hillard, we talk about intensive, extensive variables. Intensive means it depends on the size. Intensive does not. One intensive variable does not depend on the size of the system. Okay. However, that's confusing, as you will see that, because you can normalize the volume, right? You can normalize the moles, you can normalize entropy, change from an extensive variable to an intensive variable. But they're the same variables. Okay. So that's why Max suggests we should not use this intensive, extensive variables definition. Rather, we should use potentials and molar quantities. Okay. So what happens is that we have these two types of variables. One is YA, one is dXA. So what are the XA? XA are the ones in the differential. As you can see, you have them here now, right? So that's the S, V, and Ni. So they're in the differentials in the combined law, use internal energy. Of course, you can also talk about the strain and electrical and magnetic displacements too. Okay. Because they are also you can say size dependent, but you can all normalize them. Okay. And then other type of variables are the potentials. The potentials are the ones in front of the differentials. So we have temperature. Remember, we have the minus here. Okay, minus P is very important. Minus P because it's what the surroundings does to the system. So it's a compressor system. And then I have mu I. Okay. Oh, we can also have stress. So you have strain stress. Okay. And you have electrical field. You have electric displacement, magnetic field, magnetic displacements. Okay. Of course, you can see that the YA and XA are related by differentials. That's what we can define here. So it's YA, right? It's the differential of internal energy to XA. However, it's also very important to realize that U is a function of all molar quantities, right? all molar quantities. So that means YA is also a function of all molar quantities. Okay, if you change, that's what we talk about here, right? So if you change a molar quantity, other potential will change too. Okay, but you can independently change V and Ni, but not S. Okay, not S, right? Because S is a function of Ni. Okay? It's a function of Ni. We can also think about a function volume too, but that we'll talk about them later. Okay, so now we remember that we had this, if we go back to the previous slide, okay, and we have this a US function of, right, US function of S and V and Ni, okay. We had one issue there already, right? It's very difficult to control S, as we mentioned before. So then you can switch variables, because remember this S, right, T equal to U to S derivative, right? So we can switch this one. Of course, we're going to switch T later, but also we have the minus P equal to U to V derivative, right? Okay. So we can switch variables through this mathematical operation. So first one, we switch it's the P and V, okay, because this relates to the heat. So we define this new quantity, it's called enthalpy. So it's U plus PV. Then from the mathematical operation, we know du would be du plus pdv and plus vdp, because p and v are both two variables. You're going to do the full differential. Then remember that we have this equation before, and now we have the u. So we have this, basically we have two of them here, right? So this one and that one, they will cancel each other, right? Because one's negative, one's positive. You put them together, they cancel each other, then you got the new equation. This is also combined law. But now we have two variables. We have to switch a variable from V to minus P. So it is variable. Now get a DH now. Okay. So this is a fundamental characteristic of fundamental equation function, as Max put it, and also actually Gibbs put it in 1870s too. He called it fundamental equations. Now we get natural variables. Again, we call the natural variables is because they come out from our combined law. Okay, now that means H is a function of S, P, and Ni. Now, one difference now in the U here, U is a function of S and V and Ni. These are all molar quantities, right? They're all molar quantities. Okay, now one of them now is potential. Okay, so it's different now. One is the potential, that's the pressure. All right, so now we can calculate chemical potential again, but this time it's through the derivative of H, the enthalpy, but with the P fixed. Okay. Now, if you fix P, let me fix the pressure. If you add mass into it, right? So you add mass into it, as we talked about before. Okay. Now you fix P. You say dP equal to 0, or d minus P equal to 0, and then the volume must change, right? If the volume change, the system must do the work to the surroundings. Okay, so now that means first we still have a heat exchange, because if we fix entropy, we have to get the heat out of the system. So it's minus, because we have this one is larger than 0, right? Positive. So this is negative. Negative means the system will give heat out to the surroundings. And because volume changes too, so the system must do work to the surroundings too. Okay, so that might work. So because each mass has a volume, so we define a quantity called partial volume, which is volume change as a function of mass of Ni, called partial volume. And in the partial volume, that means system has to expand, right? Okay, system expands, that means system does work to the surroundings. So system will lose the energy. That's why I have a negative sign here. Okay. So this is less than 0 because system loses energy, and this is less than 0. So under this condition, there's two exchanges between the system and its surroundings, the heat and work. So now we switch one variable. Now we're going to switch it to another one. Okay. So this time we define another function called homeostatic energy. in the literature, people say home has a free energy. That's what it had before, but it recently has been suggested to remove the free energy because the free energy basically represents all the energies except the internal energy. We call it Helmholtz energy and it Gibbs energy or some other energies as we will see later. So if we do this one, then we can do the same mathematical operation. You have two differentials now, right? We have the dt and dt and ds, put them together. And then we have our combined law. To start with our combined law, you see, use in terms of internal energy. And then we get the new characteristic function, okay? And this Helmholtz energy has its natural variables as t, v, and I. Now remember, this is the potential, right? We have now a potential, okay? And two sets of molar quantities and one potential. Now we can do the partial derivatives too. Now will be the derivative of the Helmholtz energy to Ni gives the chemical potential mu I. This time we fix the temperature, okay? Temperature fixed, okay? Now again, you see you add a dNi into it, okay? And then now because we want to keep the temperature same, okay? And because dNi brings energy into it, right? Okay. So system is going to need to release the heat. We can do the same equation. It's again the same amount of heat has to be released out to keep the temperature same. And then there's no work, right? Because volume is fixed. So PdV is equal to 0. So there's no work. Okay, the next one is the Gibbs energy. Again, the free is removed based on the neonium UIP, the pure chemistry neonium recommendation. All right, so now we now have get the same mass. Now we have we use F here instead, right? Because F, remember F equal to U minus TS, okay? So that means G is equal to U minus TS plus PV. So two terms combined together, but we use F because we had F already. Okay, so that's what we had. We had F already as a function of a temperature, volume, and Ni. So now we put this into the equation. We got the combined law. This is what we see the most often in the textbook. And now the Gibbs energy is a function of temperature minus P. Of course, you can do P too. It's okay. But a lot of equations will be simpler if you use minus P. Now, two potentials now, temperature and pressure and Ni. So this natural variables are very important because those are the variables we control in experiments, right? So that's why we use the Gibbs energy the most in terms of experiments. But however, when we do the computational work, it's easy to fix the volume. That's why in the physics domain, people use Helmholtz energy mostly, but they're exchangeable, right? Just use this equation. You can, if you know one, you can calculate another one. Okay, vice versa. Okay, now we do the chemical potential. Okay, it gives energy to the derivative, to the Ni derivative. Now we fix now temperature, right? We fix temperature and pressure and add other components. Okay, but now because we fix temperature, then we're gonna have to exchange heat. We fix the pressure, we have to change the volume, and that means we have to exchange heat. This is the value we have, and also we have to do work. Okay, exchange work. And both of them have to exchange to keep this condition. Okay. But of course, that's typically how we do experiments. And however, we can define a very general free energy, just like just say we can minus whatever quantities we want to control. Okay. For example, if you do oxidation, you want to control the oxygen chemical potential, right? Instead of the oxygen content, or it's very difficult to control oxygen content, right? Or you do nitriding or carburization, you will control the carbon potential or nitrogen potential. So in that case, you can say the example, we want to control the chemical potential of any one component A. Okay, we start with Gibbs energy. Okay, so we have phi equal to a Gibbs energy minus mu a n a. Oh, I may have it here already. Let me see. Yeah, that's right. So you see, we start with Gibbs energy reason because we control temperature, and pressure, and the mass. But in some cases, we control the chemical potential of a component, right? So we define them like if you this make the Gibbs energy, then we subtract another chemical potential times Na. Then we derive the equation. Okay. Now, if you remember that this would be the temperature, pressure, now we have another chemical potential. Now we have three potentials as natural variables. Okay. So that's what we have there. Again, this is for the practical usefulness was to derive those equations so we can better use the knowledge for the practical usefulness. And I then can define the chemical potential of other components, right, which are not fixed. This time we're going to have three potentials fixed, T, P, mu, A, and then other molar quantities. Now we have to exchange heat, right? That's because temperature fixed. We have to do some work. The system has to do some work because it fixes the pressure. Now you have to exchange the components too, because if you keep the chemical potential of that component fixed. All right, so that's what we have for lecture 5. See you at the next lecture. Thank you very much.